Hi, my name is Tom and you are at level 12 out of 30 easy steps to learn everything about Einstein's special relativity. This level deals with waves. Waves are everywhere and we need a little bit more understanding about the different types of waves and how we can detect if something is a wave, yes or no. Are you into the waves? Let's go. GP, hit it! In real life, not just in imaginary physics, waves are everywhere, and that's the topic of this level. Let's start with this wave. That might be familiar to you when you go to the gym. You see people pulling the ropes up and down to train their body. So this is some kind of wave that travels through the rope. I made an animation, of course. Here it is. So you're pulling the rope up and down and the wave propagates through the rope until the end. So this is an example of a wave. This is what we call a transverse wave, which means that the up and down is perpendicular to the velocity of the wave. So the wave goes from left to right, but the stuff that's actually going oscillates is the rope. And the rope goes up and down, which is not the same direction as the wave. And that's what we call a transverse wave. It has some characteristics. Don't be shy. We are not going to do heavy math just now. It's just easy. The length at which it goes up and down is what we call amplitude. We saw the wave moving from left to right at a certain velocity. And if you take one cycle of the wave and you measure how long that is, that's something we call the wavelength. And with these three things, you can fully describe this wave. How much it's going up and down, how fast it goes through I would say the wire, but in this case the rope, and how strong or how big the wavelength is. And this is all there is to it, waves. Let's see. Another really familiar wave, of course, are the waves in the ocean when we go to the beach. You can see that the rope is more like a one-dimensional wave because it's one dimension, the dimension of the rope. But here I made an animation again and I put a frame of reference in there. The ocean, if it's perfect waves, they would go up and down. And it's like there are many ropes next to each other and you get this pattern. But another very familiar type of wave, of course, is when we drop a droplet of water or a brick into the water and we see these circular waves. So this is my animation. I have to say it's not perfect. It's not obeying all laws of physics, but it gives you an idea. So the drop will drop, boom. And you see the waves spreading out and slowly stopping. And the water is a flat surface again. So this is waves. Transverse waves. We all know these. And now comes the thing. And this is a little bit more difficult, but just try to understand the concept. Let's say you're a physicist. You do an experiment and you write down the results in some kind of table. We did this, I think, at level number 2 when we talked about algebra. Experiment, measurements, observations, writing them down in a table. How do you know if there is something wavy in your experiment? Well, if it was the rope, you could just see it with your eyes. You would actually see the wave going through the rope in the gym. Same for the water waves, right? You can actually see it. But in physics, we deal with things sometimes that we can't see. We can detect with other devices, but not with our own senses. And the results might be very complicated if you write them down on a table. And still you want to know whether that is a wave or not. And now we are going to meet two great mathematicians who found a way to detect a wave in the written observations. So here we go. The first one is D'Alembert. Let me see. he is considered, well, you know, if you saw other levels, we are ranking the stars. This is a star, and he is among the 100 greatest scientists ever. And he is a very, very good mathematician. He's at number 37 out of the 50 greatest mathematicians, according to some ranking, right? There are many rankings on the internet, but I picked one, and this is what it is. And he said, just give me your table with observations. And from a mathematical point of view, it might look complex, but the y is here, for instance, the position of the rope going up and down. And well, if you pick a point along the rope, which will be the x coordinate, so you pick somewhere along and you pick a time, then this formula will tell you at that time, at that location, where the rope is, up and down, etc. So this is a way of describing a generic one-dimensional transversal wave. You don't really need this, but just know that mathematicians are able to translate your observations from the experiment into algebraic equations. And then D'Alembert said, well, this looks very complicated, right? But we have seen this in previous levels, but if you would take the second derivative of the y locations with respect to time, and you would do the same, the second derivative of the y location with respect to the x coordinate along the rope, and you find out in your table of your experiment they are the same except for some constant, then you know two things. One, we have a wave, there's something wavy in my experiment, and number two, the constant will be the square of the velocity of the wave moving through the rope. And this was a really big achievement in math in 1746. So now we have tools to detect waves. If you want to know a little bit more, I do some background, we talked about these derivatives and these strange crooked d's in there in level number 4. And we also talked a little bit about it in level number 5 when we met Galileo, and we talked about kinematics, location, velocity, acceleration, kinematics. So this is for the one-dimensional wave, the wave going through the rope. What about three-dimensional waves? Now it gets really complicated because we humans are not fit to see in 3 dimensions while time is also another dimension. So we have like 4 dimensions and it's really difficult to envision it in our heads. But there is Leonhard Euler. Well, hold on to your seats when we go to the rankings. He is considered the second greatest scientist of all times, according to some ranking, right? But he is really, really good, and he is considered the greatest mathematician. So here he is, the guy who is the greatest mathematician of all times. And he tried to take the equation from D'Alembert and make it into a 3-dimensional one. And I think it took like 10 years or so, but here we see how we could describe mathematically how a 3-dimensional phenomena could be expressed. It looks very much like a vector field, and you should be familiar with vector fields. In level 3 we talked about vector fields. So here we have a vector with 3 components, q, r and s. Q is the vector component in the x direction, r is the vector component in the y direction, s is the vector component in the z direction. And all these 3 components can be something wavy, right? Described by some equation. Well, let's say you take another experiment, you write down the q and the r and the s for different times at different locations. You go to Euler and you ask him, tell me if there's something wavy in my experiments. And he will do this. And that's why he's a mathematician, We don't have to bother. Just tell us, Euler, give us an answer. And if he does this, and this is true, and it's a little bit the same as the example, then the answer is yes, Tom. your experiment has something wavy in it, because this holds true. Here we see the second derivative of the vector field to time on the left hand side of the equation, and on the right hand side we see this mysterious triangle again. If you watched level number 7 about divergence, curl, cross products and dot products, you know exactly what this NAPLA thingy is. But in this case they squared it, which is like a little bit different, and they called it, let me see, the vector Laplacian. You can just forget about it. It's just mathematical magic. If you want to know a little bit more about what these things actually are, you can go back to level number 3 and level number 7. But just remember, you give Euler your experimental results, he will do some voodoo and come back to you and tell you yes or no, there is some wavy stuff in your experiment. So this is it. We have mastered wave detectors. Let's move on. There are different types of waves. The one in the rope, the up and down, is perpendicular to the traveling of the wave through the rope, right? So, and that's why we called it transverse. But we also have the longitudinal wave. And there, the up and down is in the same direction as the velocity of the wave. And to visualize it, I have here 2 springs. The top one will do the classical transfer wave, so you just take the string and you're moving it up and down. But the bottom one will be the longitudinal wave, because we are pushing, we give it a boost, we push the spring, and the displacement will move in the same direction as the velocity. Here we go. So that's it, a longitudinal wave. The oscillations, the stuff that goes up and down, is in the same direction as the wave itself. Well, there is one very famous physical phenomena that's not a transverse wave, but a longitudinal wave. Which is it? Sound. Sound is a longitudinal wave. The medium is the air. If I'm speaking, I'm bringing oscillations in the air. They move in the same direction as the wave. They hit someone else's ear and they make the, I'm not sure what it's called in English, the membrane in there. It goes, it picks up on the oscillations. And these oscillations are interpreted in our brains as sound. So sound is a longitudinal wave. There it is. Let's look a little bit more about the timeline. I like timelines because it puts things in perspective, and in particular we will look a little bit at sound. So way back, before Christ, Pythagoras, who we will meet in future levels as well, he started to figure things out. He said, well, if you have a string, like something on a guitar, and you do ping, he said, I'm guessing that the pitch at which I hear the tone has a relationship with the frequency of the wave. So how fast the wave is going up and down. If it goes up and down really fast, the pitch is high. And if it's really low, the pitch is low. So that was already discovered, that there is a relationship between the two. Then, way later, in 1600, we meet Galileo again, from previous levels. And he also says there is some connection between vibrations and pitch and sounds. Okay, cool. Then in 1660, Boyle, he did something really interesting. You have to know, at that time they did not know that a wave travels through some kind of medium, or they were experimenting with this. And if you take sound needs some matter, some medium to oscillate. In this case, air, when I'm talking to you. But it could be water. It could be anything other stuff from that's physical material. You can grab it and that is being oscillated. And then he said, what would happen if I tried to bring sound through vacuum? So I have a vacuum volume, I take all the air, there are no air particles in there, there's nothing in there, vacuum. Will sound go through the vacuum? No. Let's say you are in a vacuum room, which is not a good idea because your body and your head will explode, but let's say you could, you will hear no noise because the noise needs the air to oscillate. So this was a really important discovery. Because, this is what it is. They were not thinking of sound as being an oscillation of air. They were thinking, and this is so much fun, they were thinking that sound was like a particle that moved from my mouth to your ear. So it was not an oscillation of anything, no, it was physically, I am spreading like... Well, I'm taping this in the middle of the COVID crisis, so I'm spreading things from my mouth and they enter your ear and they tell your ear what Tom is talking about. That was their worldview of sound. But then they took away, they did the vacuum experiment and then they said, particles could just travel through vacuum, right? A COVID virus could go through the vacuum, But sound stops. So maybe it's something else. It's an oscillation of some medium. So this was a big breakthrough. And then Newton, our hero, the biggest and the greatest of all, he wrote his Principia, one of the most defining publications ever. And he did the math on the oscillation and the velocity of a wave. So he could make things like, we have the wavelength and the velocity and the amplitude, and he saw relationships between them, mathematical relationships. And that's why Newton is the greatest, because he found out this, many other things as well. If I ask you how fast is sound moving, we all learn maybe as a child that it's around 300 meters per second. So when you hear the thunder and you see the flashlight when the weather is bad, you first see the flashlight, and me as a child, I started counting. 1, 2, 3, and then I heard the thunder. And if it was like 3 seconds, I would say, okay, it's 3 seconds times 300 meters, which is 900 meters. So the thunder is approximately 1 kilometer away from me. And then another flash, and I did 1, 2, boom, and I heard the thunder. And it's closing in on me. Now it's 600 meters away. So that's what we know about the speed of sound. But in different mediums, it's different. Sound in water travels way faster, 1480 meters per second. Why? Because the water is more dense than air. I don't know what this thing is called in my throat, but the one that oscillates the air, it's lazy, will oscillate, but the water is much more dense, so, it will oscillate faster, it will propagate the wave faster. If you take iron, which is much more denser again, the speed of sound goes up all the way to over 5 kilometers per second. And let's say you would have a diamond of 12 kilometers long, you would be very wealthy, and you could actually measure that it just takes 1 second for sound to go from the left end of your diamond all the way to the right end of your diamond, a diamond of 12 kilometers of length. So, then, way later, we met D'Alembert, we just discussed him. He found a mathematical way to actually detect waves in experimental results. And 10 years later, Euler did the same for three-dimensional physical phenomena like sound. So, this is it. Waves and wave detectors. It's decision time. You now know enough to proceed to the next level. You are good to go. Take the elevator. But if you are brave and curious and want to know more, you stick around and you take the stairs. It's up to you. Good for those who are still watching. Let's dive a little bit more into the wave. So this is nothing new. I've shown you this picture before. A normal transversal wave has a few characteristics. It has an amplitude, a wavelength, and a velocity, and that's just basically it. But physicists came up with different characteristics as well, something called the wave number, or the wave frequency, or the wave frequency term. And sometimes they don't talk in things like wavelengths, velocities, and amplitudes, but they use these other things. And there are very basic, simple relationships between all these characteristics, and here they are. You don't have to remember this, I just want to give you the full overview. So you can calculate the wavelength if someone gives you the wave number, right? Because you take 2 times pi divided by the wave number, and then you get lambda, the wavelength. You could also calculate the wavelength if someone would have told you the velocity of the wave and the frequency of the wave, etc. So very basic, simple relationships between different characteristics. And of course, we have the one-dimensional wave equation from D'Alembert. So this is it. That was easy, right? The super bonus. You can still, escape to the next level. But if you want to do some rock climbing, you stick around. Because next we will actually apply the one-dimensional wave detector. So we are going to do some math just to see if D'Alembert was right, yes or no. Here we go. Let's say I did an experiment. I wrote down the y's for different axes and t's, different locations, different times. I wrote the y, I measured something, and I'm going to D'Alembert and I'm asking him, tell me if there's something wavy in my experiment. Well, first let's say that we take it one step back, and he looks at my table with just numbers for different times and different locations x. I wrote down different y's, and he says, well, that looks something like this. So he already knows, but let's say he's blindfolded, he doesn't know. And it turns out that my experimental results are written down, can be approximated by a function, which is some constant a, multiplied with the sine, trigonometry, we covered that, I think in level 7 as well. The sine of 2 pi divided by something called lambda, multiplied by the location x, and we subtract some constant v, which is multiplied by the time t. Let's say that was just the result of our experiment. We know, of course, that this is the mathematical description of the perfect wave, right? And you see the amplitude a, the wavelength lambda, and the velocity v in there. It could have been, just the sinus of something. But in this case, it's exactly the mathematical equation for a one-dimensional wave. Well, let's see if D'Alembert was right. Let's apply his detector. His detector is like this. So we have to do 2 things. Well, 3 things. We have to take the second derivative of the y with respect to time. That's the left hand of the equation. We have to do it again, but now the second derivative of y with respect to the x direction. And then we need to compare those results, and if those results are the same except for some constant, which is here the square of v, then yes, we have a wave. So let's do it. So this is a little bit of, well, that's why it's a super bonus. You do need to know how to take derivatives, and you do need to know how to apply chain ruling. I'm not gonna, it's outside of the, outside this Einstein mountain, so I'm not gonna explain it, but here it is. So you take the second derivative with respect to time, and you get another function, minus v squared times the amplitude times the sine of the same thing we had before. We can do this also in the x direction with respect to the x coordinates, and if you do that, you get minus amplitude a multiplied by the sine of the stuff. And if you now compare both of them, you will see that they differ with just v squared. Et voilà, we have a one-dimensional wave. Thank you, D'Alembert, and thank you, Euler, for making this possible. You, viewers, I want to thank you as well. This was, I think, an easy level compared to all the previous levels, and I hope to see you next time. GP, hit it!